Continuation of network theory concepts. This is lecture 2 on network theory. With respect to chapter 1, I started the discussion of basic quantities, and I discussed about what exactly charge, what is current density, drift speed, mobility, and these are completed. Now we have to see what exactly electric field, what is potential difference, what is the work done, what is energy, and what is the power. Students, we know that if you take any charge near the charge, it may be positive charge or negative charge. Surrounding this charge, it produces some force. Surrounding this charge, the charge produces some force. That is, electric field is a force produced by a charge nearer its surroundings. That is called electric field. That is, I given electric field is a force produced by a charge near its surroundings. If any charge is bring nearer to this vicinity, then it experiences a force. There is a positive charge and there is a negative charge. Due to positive charge, the electric field from an isolated positive charge is outward direction. The electric field is acting in outward direction. Like this. The electric field from an isolated negative charge is, this is acting in inwards. Electric field due to a charge at a point is the force that unit positive charge would experience at that point. Then what are the units of electric field, friends? Electric field is force per unit charge. What is the force? What are the units of force? It is newtons. What are the units of charge? Coulombs. Then what are the units of electric field? That is Newton per coulomb. This is a minimum fundamentals to understand the what is the potential, what is the potential difference. Electric potential. Here potential is nothing but a voltage difference. Here I am explaining the potential difference is nothing but a voltage difference. Voltage difference. What are the properties of electric field lines? This is the basic concept that you studied even in the physics also. The field lines never intersect each other. If you take any field line, electric field line, these field lines never intersect. The field line, that is electric field lines, are the perpendicular to the surface of the charge. Always these are the perpendicular to the surface. The magnitude of charge and the number of field lines, both are proportional to each other. That is, if the field lines are increases, if the charge is increases, the number of electric field lines also increases. The number of electric field lines also increases. The magnitude of charge and the number of field lines, both are directly proportional. The start point of the field line is at the positive charge. Very important, students. This is the gunshot point. Where the field lines will start at positive charge, and end point is the negative charge. This you see, both are positive charge. Then the field lines are away from the positive charge, means starting at positive charge. It is starting at positive charge means where it ends at a negative charge. If you see, this is the negative charge, this is the positive charge. The field lines are moving from positive charge to negative charge. The field lines are moving from positive charge to negative charge. This is one of the property of the electric field lines. For the field lines to either start or end at infinity, a single charge must be used. For the existence of the field lines, there must be a charge. Otherwise, there is no electric field lines. Electric field lines do not pass through the conductor. This indicates that the electric fields within the conductor is zero. Based on this statement, also question is there, students. Internally, what is the electric field? The electric field equal to zero. The electric field lines do not pass through the conductor. This indicates that electric field lines within the conductor, the electric field within the conductor is zero. This minimum basic, even you studied in the EMTL also. This EMF subject for electrical students, EMTL subject for EC students. This minimum knowledge. Yes, students. The electric field vector E is the tangent to the electric field lines at each point. That line has the direction same that of the electric field. That is, if you draw any tangent on the electric field lines, if you draw any tangent on the electric field lines, the direction of the tangent indicates the direction of the electric field. On electric field lines, if you draw any tangent, the direction of the tangent indicates the direction of the electric field. These are the properties of electric field lines. And one more important observation, friends, that you have to concentrate. If you take any positive charge, then due to this positive charge, what is the electric field on point P? What is the electric field on point P? For a positive charge, the electric field at point P is radially outward direction. I told already, the electric field lines are moving away from the positive charge, outward direction. That's why, due to positive charge Q, what is the electric field on point P? This is in the outward direction. If you take any negative charge, friends, due to this negative charge, what is the electric field on point P? We know that the electric field lines are ends at negative charge, moving towards the negative charge. That's the reason why, due to negative charge, the electric field on point P is inward direction, radially inward. For a negative source, the electric field at point P on Q radially inward direction. Due to positive charge, it is moving, it is acting, the electric field is acting radially outward direction. Due to negative charge, the electric field is acting radially inward direction. The reason, you know, always with respect to negative charge, the field lines are towards the charge. With respect to positive charge, the field lines are away from the charge. See the one more observation. Let this is the positive charge. This positive charge is placed in an electric field. If the positive charge is placed in an electric field, now we are placing the positive charge in electric field. Then what is the force on charge? The force on charge equal to E bar into Q. The force on the charge equal to E bar into Q. Correct? E bar into Q. That is because it's a positive charge. It is not electron. It is a positive charge. That is, if any positive charge is placed on the electric field, the force is in the direction of the electric field. But in the starting of yesterday class, I told F equal to minus E bar into E. Why I taken this negative sign? Where that is the electron. That is the negative charge. Because of that, I taken this negative. Force and electric field is opposite if it is electron. If it is a positive charge, force and electric field in the same direction. Force and electric field in the same direction. That is, positive charge Q placed in electric field, the force on Q in the direction of E. The force on Q in the direction of E because of positive charge. If you place any negative charge in electric field, then what is the force on negative charge? The force on negative charge equal to minus E bar into Q. If it is minus E bar into Q, the force opposite to electric field. The direction of electric field and force is opposite. The direction of electric field and force is opposite. Every observation is very important, friends, to answer any theory question, to answer any statement-based questions. Negative charge Q placed in electric field, the force on Q opposite direction of electric field. With this knowledge, now I am defining what is electrical potential and potential difference. I am explaining the electric potential means I am defining the voltage. I am defining the potential difference means I am explaining the voltage difference. Voltage difference. Potential difference or voltage difference. Potential or voltage difference. Friends, to clearly understood what exactly potential, what exactly voltage. Let's consider an arbitrary electric field due to any charged object. This is the electric field. Now, let at point A, I taken a positive charge Q. Now we have to move this positive charge from A to B through electric field. Now we have to move this positive charge from A to B through electric field. We know that whenever this charge is entered into electric field, there is a force on the charge. Whenever charge is placed in an electric field and a charge, there is a force is produced. Now what I am telling, if you have to move this charge from A to B, at every point of electric field, a force is produced on the charge. Whenever force is produced on the charge, we have to apply the force, we have to apply the external force in such a way that we have to overcome that force and move this charge from A to B. Clear, sir? Whenever this charge is entered into electric field, there is a force is produced. Now I have to move this charge now. If you have to move this charge, we have to apply some external force. Then only the charge is moving. This I am giving. If you move plus Q from A to B, at each point of electric field, it experiences a force of EQ. This is a positive charge now, that's why plus EQ. To move the charge from A to B, we have to apply some external force opposite to F. We have to apply external force opposite to this one. Once we can overcome this force, then only the charge is moving. Then what is this external force, friends? The external force equal to minus E bar into Q. Why take a negative sign here? Here the force is plus, positive. We are applying opposite force means negative. Then we can overcome this force, then only charge is moving. That's why what is the external force? External force equal to minus E bar into Q. That means we are applying some external force means we are doing some work. Because of this external force, there is some work is done. What work is done here, friends? There is a movement of the charge. We are applying some external force. Because of that external force, there is some work done. What is the work done here? There is a movement of the charge. Then work done by external force. I am calculating what is the work done by external force. External force into, what is the work done? Force into displacement. Work done is nothing but a force into displacement. Force into external force into, let's assume that charge is moving for a length of dl. Then F external into dl. What the external force is applied? Minus E bar into Q. The displacement is dl. Then the external work done by external force. This is the work done by external force. Then I'm integrating this. In work done means we are moving the charge from point A to point B. From point A to point B. External force into displacement. What is the external force? Minus E bar into Q. This I substitute. Then this is the external work done. That is the work done by external force. This is the work done by external force. This is work done by external force. And this is the work done by electric field. This is the work done by electric field. Externally, we are applying this force for the movement of the charge from A to B. Because of electric field also, there is a force is produced. Because of that force, what is the work done? This is the work done by electric field. With this knowledge, students, any doubt? Any doubt, sir? All of you understood? Balaji, Kavya, any doubt? Soham, clear, sir? We are applying some external force. Because of that external force, there is some work done. Why we have to apply the external force? For the movement of the charge by overcoming the force due to electric field. That's why we are applying the external force. Due to that external force, this is the external work. Now, what is the electric potential? With this knowledge, now you have to define the electric potential. The electric potential are voltage. Electric potential are voltage. If you choose the initial point at infinity, let us assume that the charge is at infinity position and final point is at P. Instead of A and B position, I am taking the infinity to some point P. Work done by external agent or negative of work done by the electric field, electrostatic field. Work done by external agent or it is equal to negative of work done by electrostatic field. Correct or not? This is minus, this is plus. This W external equal to minus W. Correct, friends? W external equal to minus W. Work done by external agent equal to negative of work done by electric field. Negative of work done by electric field. Negative of work done by electric field. W external equal to minus Q infinity to B. Instead of A to B, in order to define the potential, in order to define the voltage, I am taking we are moving the charge from infinite position to point B. Actually, here I given A to B position, but to define the potential or to define the voltage, friends, let us assume that the charge is at infinite position. We are moving the charge from infinite position to point B. Then this is the W external. Then what is the potential at point P? Let us assume that this is the electric field. This is the electric field. Now, at infinite position, charge is present. Now we are moving the charge from infinite position to point Q. Point Q. For this, there is some work done. Then how to define the electric potential at point P? This is point P. The electric potential at point P is work done per unit charge. Work done per unit charge. External work done per unit charge. The work done by external force per unit charge. This work done for the movement of the charge from infinity to point. This work done per unit charge. What is the work done, friends? This is the work done. Infinity to P, E bar dl. This is minus Q. Q cancel. Then this is the potential at point P. This is the potential at Now here I am giving the What is the exact definition of the electric potential? The work done by external agent in slowly bringing a unit positive point charge from infinity to the observation point, or potential as the external work done by unit charge, potential energy per unit charge. This is called electric potential. Therefore, the simple formula for potential or voltage, all of you well know this formula. Potential or voltage V equal to W by Q. Work done per unit charge. Work done per unit charge. This is the voltage or potential. V equal to W by Q. How this formula we got? This is the concept. Students, concept very simple. If you have to move the charge in electric field, we have to apply the force, external force, in such a way that we have to overcome the force due to electric field. Then we can move the charge from one point to another point. For the movement of the charge from one point to another point, there is some work done now. That work done per unit charge for the movement of unit charge is nothing but a potential or voltage. To define the potential, you take from infinite position. To define the potential difference, you take 2 points. See the difference. What is the difference between potential and potential difference? To define the potential, we have to take from infinity to some point B. To define the potential difference, we have to take from A to B. Between the 2 points, we are moving the charge. That corresponding to potential difference. We are moving the charge from infinity to some observer point or some point B. Then that is nothing but a potential. Now here I am giving the potential difference also. What is the potential difference? The potential difference between points A and B can be defined as, see the difference, friends, how we can define the potential and potential difference. Yes, the potential difference between points A and B, can be defined as work done by an external agent is slowly shifting a unit positive charge between points A and B. Therefore, the potential difference equal to, we are shifting the charge from A to B minus Q E bar into dl. Then VB minus VA, the potential difference VB minus VA equal to A to B, this Q cancel now. Then A to B minus E bar into dl. This is E bar into dl. We can also write E into dl cos theta. What is this theta here? Where theta is the angle between E bar and dl. Okay, this is the potential difference. The potential difference equal to VB minus VA. See the difference between the potential and potential difference. Both are work done per unit charge. For the movement of the charge from infinity to some observer point, that is potential. Potential difference is nothing but we have to move the charge between 2 points. Yeah, that is nothing but a potential difference. Yes, for example, in this case, if W external greater than 0, if it is a greater than 0, what about VB greater than VA? If VB greater than VA, then B is at high potential. If W external less than 0, then VB less than V. Then A is at high potential. Correct? This is the positive, VB greater than VA. This is the negative, VB less than VA. If W external equal to 0, work done is 0, then VB equal to V. Then the potential difference is also 0. Work done 0 means the potential difference is also 0. But here I have to give very important observation. That is very important to solve the statement-based questions. To answer the concept-oriented questions, friends, statement-based questions, this observation is important. Concentration. What is VB minus VA, sir? VB minus VA equal to, what is the formula given? Minus integral A to B E dl cos theta. If theta equal to 180 degrees, can anybody? If theta equal to 180 degrees, cos 180 is how much, sir? Minus 1. If it is a minus 1, minus into minus plus. That is VB minus VA greater than 0. Then VB greater than VA. Listen, sir. Please concentrate. I taken theta is 180. Cos 180 minus 1. Minus into minus plus. This VB minus VA is plus now. This is positive now. This is positive. Cos 180 minus 1, sir. This minus into minus plus. VB minus VA is positive. VB minus VA is positive means VB minus VA is positive means VB minus VA is positive. That is VB minus VA, then VB greater than VA. VB greater than VA means we are moving from A to B now. We are moving from A to B. VB greater than VA means potential is increasing or decreasing. Potential is increasing or decreasing, sir. Potential is increasing. VB greater than VA means potential is increasing. Now tell the students. 180 degrees means if you are moving opposite to electric field, if you are moving opposite to electric field, if you are moving, students, if you are moving opposite to electric field, opposite to electric field, opposite to electric field, opposite 180 degrees now, electric field. Potential is increasing or decreasing? Potential increasing. Potential is. Why taken? Because VB greater than VA, final point is more voltage. Final point is more voltage means potential is increasing. If you are moving opposite to electric field, potential is increases. Now tell us, friends, if theta equal 0 degrees, sir, what is cos 0? 1. Cos 0, 1 means positive. Cos is positive. Already this is negative. Negative into positive, negative. Then what is VB minus VA, friends? VB minus VA is negative. VB minus VA is negative means VB minus VA less than 0. Then VB less than final point. The final voltage is more or less less. Theta equal 0 means in the direction of electric field. If you are moving, what is theta, sir? Theta is the angle between E bar and DL. E bar and DL, sir. DL is the displacement. Theta equal to 0 degrees means E bar and DL is same direction. We are moving in the same direction. Theta equal to 180 degrees means, what do you mean by theta equal to 180 degrees, friends? E bar and DL is opposite direction. If you are moving opposite electric field, potential will increase. If you are moving in the direction of electric field, in the direction of electric field, in the direction of electric field, if you are moving in the direction of electric field, what is the potential? Potential is decreases. Potential is decreases. If you are moving opposite to electric field, potential will increases. If you are moving in the direction of electric field, the potential is decreases. Sir, one simple observation. What is potential? For these two statements, what is the potential work done per unit charge? Now what I am telling, if you are moving opposite to electric field, if you are moving opposite to electric field, you have to do more work or less work? Come on, sir. You have to do more work or less work? More work. Then potential is increases. If you are moving in the direction of electric field, in the direction of electric field, less work done. Less work done, voltage will reduce. This is the observation. Understand the point? If you are moving opposite to electric field, to overcome that, you have to apply more force. More work you have to do. If you are moving in the direction of electric field, less work. If less work, if it is decreases, voltage also decreases. Less work done, less voltage. More work done, more voltage. That is the point I am telling. Clear, friends? Okay, this is very important observations that you have to consider. Now, with this knowledge, I have to give two more statements. Yes. A negative charge, if you take any negative charge tries to move, negative charge tries to move. Can anybody tell the students? Negative charge tries to move opposite to electric field or in the direction of electric field? Can anybody? Negative charge is placed in electric field. It is moving in the same direction or opposite direction of electric field? Come on, I'm expecting answer from you. I'm talking about with respect to negative charge. Negative charge tries to move. This is electric field, sir. In this electric field, I place negative charge. Then it moving in the direction of electric field or opposite to electric field? Force equal to minus, clearly I'm writing. This is electric field, friends. This point I already given this. I am placing negative charge. What the force? Minus E bar into Q na. Then force, electric field is this direction. Force is. Always charge is moving in the direction of force only na. That means negative charge tries to move opposite to electric field. Opposite to electric field. Opposite to electric field. What do you mean by opposite to electric field? What the meaning of this sentence, friends? Opposite to electric field means what the meaning of this sentence? If you are moving opposite to electric field, what about the voltage? Increasing. That is R in the direction of, in the direction of, in the direction of, opposite to electric field means in the direction of increasing potential. In the direction of increasing potential. In the direction of increasing potential. Increasing potential. In the direction of increasing potential means R. In the direction of increasing potential means we are moving from low voltage to high voltage. Or from low to high voltage. Low voltage to high voltage. That is, negative charge is always move from low voltage to high voltage. See the friends. See the concept. See the concepts are negative charge. Take the electron. Electron. This electron is always moves. Negative charge means electron. Electron is the negative charge. Na? Always move from low voltage to high voltage. That is the meaning. If it is the electron direction, what about the current direction, students? Current direction is opposite. That is, current is always going from high voltage to low voltage. Satisfied? Understand, sir? Negative charge tries to move opposite to electric field only. Always it is opposite to electric field only. What is the meaning of opposite to electric field? In the direction of increasing potential. The same statement I am giving like this. In the direction of increasing potential. What do you mean by in the direction of increasing potential? From low voltage to high voltage. That is, negative charge is moving always from low voltage to high voltage. Negative charge is moving from low voltage to high voltage means electrons are moving from low voltage to high voltage. Current is moving from high voltage to low voltage. I told already the current direction is opposite to electron direction. Satisfied? Okay. I'm writing one more statement. Positive charge. Can anybody tell, sir? Students. Positive charge tries to move in the direction of electric field. Why? Tries to move in the direction of electric field only. Why? This is the electric field. This is the electric field, students. If you place the positive charge, then what is the force on electric positive charge? E bar into Q. This and this is same direction. Always charge is moving in the direction of force only. That's why positive charge try to move in the direction of electric. Or it is also called which one, students? Direction of electric field means increasing potential or decreasing potential? Decreasing potential. Or in the direction of, yes, students, in the direction of decreasing potential. Decreasing potential. Decreasing potential. Or it is also called which one, students? Decreasing potential means or from high voltage to low voltage. High voltage to low voltage. High voltage to voltage. That is, the positive charge is moving from, this positive charge is moving from high voltage to low voltage. Negative charge is moving from low voltage to high. So simple, sir. Current is high voltage to low voltage. Current high to low means electron is low to high because current direction and electron direction. Okay, this is about what exactly the concept of potential and potential difference. Any doubt? Yes, friends. Any doubt? Clear? Okay. Okay, this is about potential and potential differences. Now I have to explain what is the energy. I have to explain what is the energy. What is the energy? We know that to move the charge from opposite force, to move the charge opposite to force produced by electric field, we are applying some external energy. That external agent delivers the energy to charge. Then charge absorb the energy. Then charge absorb the energy. That is, to move the charge, to move the charge, opposite to force produced by electric field. Force produced by electric field. By electric field. Force produced by electric fields. The external agent, the external agent, the external agent delivers, the external agent delivers energy to charge, energy to charge. Then charge absorbs the energy. Then charge absorbs the energy. Absorbs the energy. Then what is that charge absorbed by the energy? That is called work done or energy. Therefore, work done or energy. This is also called work done or energy. Work done or energy. You have to denote with either W or E. Work done or energy. I'm using the E notation. E equal to or W equal to. What is V equal to, friends? W by Q. Then what is the W equal to? VQ. Therefore, energy equal to V into Q. QV. Energy equal to V into Q. That equal to QV. Okay, this is energy or work done. Energy or work done. We know that to move the charge, we are applying external force. That external agent delivers the energy to charge. Then charge absorbs the energy. When the charge is absorbs the energy, then it is, this is the energy absorbed by the charge. See, for example, friends, a battery is connected. Here, battery is the external agent. Battery is the external agent. This external agent drives the charge. This external agent drives the charge. Then, where the charge getting the energy? From the battery, it is getting the energy. Who is the external agent here? Battery is the one of the example for external agent. From the battery only it is getting the energy. Then charge is moving. Then only charge is moving. Okay, that is the concept. That is to move the charge opposite to force produced by electric field. The external agent delivers the energy to charge. Then charge absorb the energy. Then what is that charge absorbed by the, what is that energy absorbed by the charge? That is E equal to W equal to. Therefore, energy supplied equal to, how you can write, friends? Energy supplied equal to charge supplied into voltage. Charge into voltage. Charge into voltage. How much energy supplied to the charge? The energy supplied to the charge equal to charge into voltage. Then one more parameter is we have to define the one more parameter is we have to define what you can write power. Then how to define the power source? The energy is transferred to the charge. The energy is transferring to the charge. Why energy is transferring to the charge? For the movement of the charge. For the movement of the charge, the energy is transferred by external agent. Battery is the one external agent. Source is the one external agent here. Yeah. Rate at which energy is transferred to the charge, that is called power. At what rate it is transferring? Rate at which energy is transferred to the charge. Energy is transferred to the charge is called power. This is called power. Then how to write the power equals, friends? Is P of T equal to, I'm writing, this is the instantaneous power. P of T equal to rate at which energy is transferred to the charge, dW by dt. dW by dt. Or you can also write dE by dt. Either E notation you have to use or W notation. dW by dt. Then shall I write like this? The power equal to dW by dt, na, rate at which energy is transferred, na, divide and multiply with the dq students. Divide and multiply with the dq. Then from this, what you can write, friends? P of T equal to dW by dt into dq by dq. Divide and multiply. These two terms I am writing dW by dq into these two terms I am writing dq by dt. dq by dt. Then P of T equal to work done per unit charge. What this is? Work done per unit charge. This rate of change of charge. Rate of change of work done with respect to charge. This is V of T. dq by dt. This is I of T. Current. Therefore, power equal to voltage into current. This is the formula. Power equal to voltage into current. This is called instantaneous power. Voltage into current. Okay, this is the power expression. All these formulas you have to use in different applications later. Instantaneous power. The instantaneous power expression equal P of T equal to V of T into this expression for instantaneous power. Yes, friends, any doubt? Please go through this. We know that power equal to power P equal to dW by dt, or it is also equal dE by dt, where E is the energy, not electric field, sir. I'm taking this is the energy. From this, how to get energy? Energy equal to or work done equal to integral P dt. Integration of power is nothing but energy. Like this also. The integration of power is nothing but energy. Integration of power is nothing but energy. That is about different basic quantities that I have to discuss. What are the different quantities, friends? Concentrate. I completed charge, current, current density, lift to speed, mobility, electric field, potential, potential difference, work done. This both are same. Energy, power. This is one concept. In chapter 1, that is fundamentals of electric circuits. This is the first topic, basic quantities. The basic quantities are completed. If you have any doubt, you please ask me, then I will explain. And with this knowledge, I'm going to start in. Before that, I have to solve two questions, then we'll start the next topic. So can anybody answer this one? Students, what is the answer? Calculate the voltage across the bulb. An energy source forces a constant current of 2 amperes for 10 seconds to flow through a bulb. If 2.3 kilojoules is given off in the form of light and heat energy, calculate the voltage across the bulb. What is the formula for V equals, friends? Work done per unit charge. V equal W by Q. W by Q equal to IT. How much energy is delivered? How much energy is given? 2.3 kilojoules. 2.3 into 10 cube. What are the current, friends? Current is 2 amperes. How many seconds? 10 seconds. Then what is the voltage? Anybody? It's approximately you can get 115 volts now. Is it correct? Voltage equal to 115 volts. Now to calculate the voltage across the bulb, voltage equal to 115 volts. Next. See the next one, friends. Find power delivered to element at t equal to 3 milliseconds. If the current entering its positive terminal is 5 cos 60 pi t amperes and voltage applied is 3 di by dt. You have to calculate the power delivered to element. How to calculate power equal to V of t into I of t squares. What the voltage it is given? 3 into di by dt into I of t 5 cos 60 pi t. 5 cos 60 pi t. 3 into di by dt 5 cos 60 pi t. You have to calculate what is 3 into di by dt. Separately I am doing. This is 3 into d by dt of what is I squares? 5 cos 60 pi t. 5 cos 60 pi t. Then if you differentiate this 5 into 3, 15. Cos differentiation is minus sine 60 pi t. Again 60 pi t is differentiated 60 pi. We differentiate 60 pi t, we can get 60 pi. This is how much you can get, friends. Come on. 15 into 60, 900. Minus 900 pi sine 60 pi t. Minus 900 pi sine 60 pi t. Now you substitute here p equal to 3 into di by dt I calculated now. This is minus 900 pi sine 60 pi t 60 pi t into 5 cos 60 pi t. 5 cos 60 pi t. Yes. Now you substitute here minus 900 pi sin 60 pi. What is the t equal to? T equal to 3 milliseconds. 3 milliseconds that you have to substitute. 3 into 10 power minus 3. 3 into 10 power minus 3 into 5 cos 60 pi t. 5 cos 60 pi t is 3 milliseconds. 3 milliseconds. Now you take this pi is 180 degrees. Take this is pi is 180 degrees. Then you simplify these students. How much we can get? Can anybody answer this? This approximately equal to minus 6.394 kilowatt you can get. Please write. Pi equal to 180 degrees you substitute. Then you tell this answer is approximately equal to minus 6.394 kilowatt. Minus 6.394 kilowatts. Clear? Any doubt? Okay, this is about two important models of questions. With this, basic quantities are complete. The next topic, how to start with Ohm's law. I think all of you will know this minimum fundamental. We are studying from this Ohm's law from 10 plus 2 also. But some observations are very important here. Yes. George Simon Ohm, a German physicist, in 1826 experimentally determined the most basic law relating to voltage and current for a resistor. What is the relation between voltage and current in a resistor? Yes. Let's consider the length of the, let's consider one conductor. Let's consider a conductor. Let's consider a conductor. This is the length of the conductor. Let L is the length of the conductor. L is the length of the conductor. You have to define, let this is the electric field. Then the voltage applied to this conductor is V. We define electric field equal to, one more formula I am giving students. What is the relation between electric field and voltage? Voltage per unit length, V by L. Voltage per unit length is nothing but a electric field, where V equal to voltage. V equal to voltage. Let the current through the conductor is I. I is the current through the conductor. We know that where L is the length of the conductor, length of conductor, A equal to cross-sectional area of conductor, cross-sectional area of conductor, cross-sectional area of conductor. Then we know that in a first form of Ohm's law, what is the first form of Ohm's law, students? J equal to sigma E. The first form of Ohm's law is J equal to sigma E. This is already given in the previous session. J is the current density, current per unit area. Sigma into what is E? Voltage per unit length. Voltage per unit length. From this, you have to write V equal to this is voltage applied across the conductor, where V equal to voltage across conductor. Voltage across conductor. I equal to current through the conductor. Current through conductor. Current through conductor. From this, what is V, friends? L by A sigma. L by A sigma. You bring this L this side, sigma this side, into I. L by A sigma into I. where this L, A and sigma are taken as a constant, L by A sigma, this is called R, this is given as a resistance. This is called resistance. Then if it is a resistance, then V equal to I into R. I am replacing this L by A sigma equal to R. Then V equal to IR. Then what is the units of this resistance? The units of this resistance is ohm, or it is denoted by symbol ohm symbol. V equal to IR. Then this is the constant. This R is the constant. Then you write as a proportionality. V is proportional to I. That means what is our observation here, friends? How much resistance is offered by the conductor? The resistance offered by the conductor depends on length, area, conductivity. These two parameters will decide the resistance of a conductor or wire. For any conductor, the resistance is depends on length of the conductor. If length of the conductor is increases, resistance is increases. If area of the conductor is increases, resistance is decreases. If conductivity increases, resistance decreases. Where sigma is the conductivity source. What is sigma here? Conductivity. Where sigma is the conductivity. We can also write the conductivity equal to, you know this relationship. Conductivity equal to 1 by resistivity. What is rho here? Resistivity. Resistivity. If you substitute conductivity equal to resistivity, 1 by resistivity, L by A into 1 by rho equal to R. This rho goes to the numerator, R equal to rho L by A. This all of you well known this part. Like this we can get this. R equal to rho L by A. Clear, friends? R equal to L by A sigma. These constants are, this is given by ohms. They taken, during explaining this one, they taken L is A and sigma is the constant. This combination will measure the resistance. Then they taken this one. R is the constant. Then if you write the proportionality, remove the constant. Then V is proportional to I. Means according to Ohm's law, the voltage applied, the current through the conductor, whatever the current is flowing through the conductor, or voltage applied across the conductor is directly proportional to current through the conductor. This statement I given. Like this, Ohm's law is given. Ohm's law states that the voltage across the conductor directly proportional to the current flowing through, provided that all physical conditions and temperature remains constant. L is constant, sigma is constant, A is constant, temperature constant. Provided that all these conditions are constant, then only V proportional to I squares. Okay, that's that I told now. By considering these are the constants, and even temperature is also constant. It is very important. Provided that all physical conditions are constant, then V is proportional to I. Therefore, according to Ohm's law, V equal to IR. V equal to IR. We can also write different forms. I equal to V by R. Or we can also write R equal to V by I. All of you know these simple formulas. R equal to V. We can also write, friends, I equal to V into G. I equal to V into G. Where 1 by R equal to G. This is called conductance. Conductance. This is called conductance. What are the units of conductance? What are the units of conductance, friends? The conductance units is ohm inverse. 1 by ohm, 1 by ohm is ohm inverse. Or it is also called mho. Mho. Or it is also called Siemens. Siemens. Yeah, this is the units of conductance. The units of conductance is ohm inverse or mho or Siemens. We know that V equal to IR, friends. We know that I equal to V into G. We can also write V equal to I into R different ways. We can also write V equal to I is dq by dt, no? dq by dt into R. Like this also you can write. In different ways of writing the form. I equal dq by dt. This is the different forms of Ohm's law. But these are the different forms of Ohm's law. Different forms of Ohm's law. Forms of Ohm's law. Ohm's law. But these laws are applicable. Voltage is applied between the terminals. If voltage is applied between the terminals, between two terminals. If voltage is applied between two terminals, between two terminals, voltage is applied between two terminals, then only this is applicable. But you know, J equal to sigma E. This is also Ohm's law, students. What this is called? First form of Ohm's law. First form of Ohm's law. This is the first form of Ohm's law. It is applied at any point in the conductor. It is applied at any point in the conductor. It is applied at any point in the conductor. At any point in the conductor. This is the difference. That's why I told already. This is mainly used in EMF. At any point in the conductor. But this formula is applicable if the voltage is applied between the terminals. Students, I told already. We know that R equal to L by sigma A, L by 1 by rho into A, that equal to rho L by A, where rho equal to resistivity, that is equal to resistivity, that is 1 by sigma, where sigma is the conductivity, not conductance, it is a conductivity. One of the formula for resistance, all of you well know this, R equal to rho L by R equal to rho L by. Now, what is the units of conductivity? Can anybody? Units of conductivity. Units of conductivity, not conductance. The units of conductivity now. How to write conductivity? How to write conductivity, sir? We know that R equal to L by A sigma. From this, sigma equal to L by AR. What are the units of length? Meter. What are the units of area? Meter square. This is ohm. Then meter cancel. 1 by ohm meter. 1 by ohm meter is ohm meter inverse. Ohm meter inverse. What are the units of resistivity? Resistivity units. What are the resistivity, students? R equal to rho L by A. From this, rho equal to RA by L. What are the units of resistance? Ohm. What are the units of area? Meter square by meter. Meter cancel. Ohm meter. Resistivity units. Resistivity units. Ohm meter. Resistivity units are ohm meter. What are the units of resistivity? Ohm meter. What are the units of conductivity? Ohm meter inverse. That is 1 by resistivity equal conductivity equal to 1 by resistivity now. That's why ohm meter. But point to remember, friends, resistivity is the property of substance, but resistance is the property of object. See the difference. Very important point. Resistivity is the property of substance. Property of substance. But resistance is the property of conductor. But resistance is the property of conductor. Property of conductor. Resistance is the property. We know that according to Ohm's law, we know that V equal to IR. Then R equal to VI, V by I. If you draw the characteristics, V versus I, we can get the linear characteristics. The slope of this curve gives the resistance. Resistance equal to V by. It is a linear characteristics. The slope remains constant. For linear characteristics, the slope remains constant. It is having the, therefore resistance is having the linear characteristics. Linear characteristics. But which is constant, friends? At constant temperature. At constant. This is applicable at constant temperature. Okay, this is about what exactly Ohm's law. But very important is, what are the limitations of Ohm's law? That is important for computer exam point. What are the limitations? That you have to concentrate. The limitations of Ohm's law. Ohm's law is not a universal law. This is because Ohm's law is only applicable to ohmic conductors, such as iron, copper. But it is not applicable to non-ohmic conductors. Ohm's law for ohmic conductors. What's your doubt? 6 plus. Any doubt? Who respond? Padma Priya? You send that 6 plus. What the meaning of that? Any doubt? Can you please respond? Okay. Ohm's law is not a universal law. This is because Ohm's law is it's a Ohm's law. It's for applicable for ohmic conductors such as iron, copper, but it's not applicable to non-ohmic conductors such as semiconductors. Ohm's law is not applicable for the semiconductors. Ohm's law does not apply semiconductor devices because they are non-linear devices. This means that the ratio of voltage to current does not remain constant for variation in voltage. In which case, semiconductors, you take diode or transistor, these are having non-linear characteristics. V by is not constant. Slope is not constant. It is a non-linear characteristics. That's why it is not applicable. This is also second limitation. Ohm's law fails to explain the behavior of semiconductor and unilateral devices such as diodes. That's why it is not applicable for semiconductor. Ohm's law may not give the desired results if the physical conditions such as temperature or pressure are not kept constant. Friends, it's very important. I told already. This is with the assumption of L by sigma A is constant. Physical parameters are constant. Physical lengths are constant. Even temperature is also constant. Ohm's law is applied only at constant temperature, not at variable temperatures. And physical dimensions are also constant. Okay, this is about what exactly Ohm's law. With this, the basic quantities, that is different basic quantities, and Ohm's law is completed. Next, I have to discuss RLC element. What is the resistance? What is the inductance? What is the capacitance? Due to some work, today I'm ending the session. Tomorrow we'll continue, friends. What are the resistors? What are the properties of resistor? What are the linear resistor? What are the non-linear resistor? All this, what are the color coding of resistors? After discussing the color codings, then we go for some formulas with respect to resistor. Then next inductance, next capacitance. After completing resistance, inductance, and capacitance discussion, then I will discuss the types of elements. What are the unilateral, bilateral, what are the active elements, passive elements. Then after discussing that, then we'll go for the KCL, KVL, nodal mesh analysis. This is the sequence, friends. Friends, any doubt? Have any doubts, sir? Do you want this PPT? You want this PPT or you are following the notes, that direct videos? Yes. Okay, if you want this PPT, yeah, just a minute. I will tell one Telegram channel. You have to join that. Every day I will share that PPT in that channel. You have to create this channel. So you have to try this. Today I will share the yesterday PPT and today PPT. Total small letters. SMART, smart gate rankers. Gate rankers. Can you try to join this? It's a public channel. SMARTGATERANKERS. Smart Gate. Can anybody try? Is it okay? Can you please respond? Is it available? Can anybody? One. Yes. Thank you. I will share just within 5 or 10 minutes. I will share this total PPT yesterday and today. Every day, please don't miss the class, friends. Continuously, every day, whatever the concepts I'm explaining, please complete that one. Day-to-day preparation. Then finally, no doubt at all. I'm telling that if you have to get more confidence on the network theory, more and more practice is required. Then only you can get the more confidence. You have to solve the more number of questions. Maximum, I'll try to give the maximum number of questions to practice. Okay, thank you. I'm ending the session.